Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should truly stretch your imagination, perhaps even to its breaking point. The universe, as we understand it, is currently estimated to be about 13.8 billion years old. That's a number so vast it's almost meaningless without context. For perspective, human civilization, from the first cities, is only about 6,000 years old. The Earth itself formed 4.5 billion years ago. Dinosaurs roamed our planet about 65 million years ago. So 13.8 billion years is an almost incomprehensible span of time. Now, combine that with another fundamental constant of our reality, the speed of light. Light, the fastest thing we know, travels at precisely 209,792, 458 meters per second in a vacuum. It takes light from the Sun about 8 minutes to reach Earth. Light from the nearest star system, Alpha Centauri, takes about 4.3 years to reach us. But here's the truly mind-bending part. Because the universe is 13.8 billion years old, and nothing can travel faster than light, there's a fundamental limit to how far back in time we can see. We can only see light that has had enough time to reach us since the beginning of the universe. This means there's an edge to what we can observe, a boundary defined not by physical walls, but by time and the speed of light. This boundary defines what we call the observable universe, a sphere of existence that stretches out in every direction for about 46.5 billion light-years. And here's the kicker, that 46.5 billion light-years is not 13.8 billion light-years, even though the universe is only 13.8 billion years old. The difference between those two numbers, and why that boundary is so much larger than the age of the universe times the speed of light, reveals a profound truth about the very fabric of space and time. It tells us that the universe is not just expanding, space itself is stretching, carrying distant galaxies further away from us even as their ancient light journeys towards us. This isn't just about big numbers, it's about the very nature of reality and what lies beyond the horizon of our perception. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's begin with a question that sounds deceptively simple. What do we mean when we say the universe? For most of human history, the universe meant everything we could see with our eyes, then everything we could see with telescopes. But modern cosmology has given us a much more precise and, frankly, much more humbling definition. When cosmologists talk about the universe, they often distinguish between two crucial concepts, the observable universe and the entire universe. The observable universe is a sphere of space centered on us, stretching out as far as light has had time to travel and reach us since the Big Bang. It's our cosmic horizon, the limit of our vision, and it has a definite quantifiable size, one that is truly staggering. Think about it this way. Imagine you're standing in a vast ancient forest. You can only see as far as the trees allow, or as far as the light reaches. If a tree falls far away, you won't hear it until the sound waves reach you. If it's too far, you might never hear it. Light works similarly, but with a fundamental speed limit. light travels at approximately 300,000 kilometers per second. This speed is constant for all observers, a cornerstone of Einstein's special relativity. Now, we know the universe began about 13.8 billion years ago, so the most distant light we could possibly detect would be light that has been travelling for 13.8 billion years. Logically, you might think, so the observable universe is 13.8 billion light-years in radius. A light-year, remember, is the distance light travels in 1 year. So 13.8 billion light-years sounds like a perfectly reasonable answer. But here's where the universe gets wonderfully, mind-bogglingly strange. The actual radius of the observable universe is not 13.8 billion light-years, but closer to 46.5 billion light-years. That's more than 3 times larger. Why the discrepancy? The answer lies in one of the most profound discoveries of the 20th century, the expansion of the universe. To understand this, we need to go back to the early 20th century, to the work of astronomers like Vesto Slipher and Edwin Hubble. Slipher in the 1910s observed that most spiral nebulae, what we now know are galaxies, were moving away from Earth. He noticed a red shift in their light, meaning the light waves were stretched, just like the pitch of an ambulance siren drops as it moves away from you. This redshift indicated they were receding. Then, in 1929, Edwin Hubble made a groundbreaking discovery. He observed that the further away a galaxy was, the faster it appeared to be receding from us. This wasn't just random motion. There was a direct proportional relationship between a galaxy's distance and its recession velocity. This became known as Hubble's law. It was the first concrete evidence that the universe was not static, but expanding. Now, here's where it gets really interesting, and where our intuition about distance and speed breaks down. The expansion of the universe isn't like galaxies flying through a pre-existing static space, like marbles scattering across a tabletop. Instead, it's space itself that is expanding, stretching, growing. Imagine you have a balloon and you draw dots on its surface. As you inflate the balloon, the dots move further apart from each other, but they aren't. Quote 8. A cross. The balloon's surface in the traditional sense. The surface itself is stretching. In the same way, galaxies aren't zooming away from us through space. The space between us and those galaxies is stretching, carrying them along for the ride. This stretching of space has a crucial consequence for light. When light from a distant galaxy begins its journey towards us, it travels at the speed of light. But during its billions of years of travel, the space it's traversing is simultaneously expanding. This means the light waves themselves get stretched out, causing the redshift Slipher observed. More importantly, it means that by the time the light finally reaches us, the galaxy that emitted it is now much, much further away than it was when the light first set out. Consider a photon of light that was emitted shortly after the Big Bang, say 13.8 billion years ago. It started its journey from a point that was, at that time, relatively close to what would eventually become our own galaxy. But as that photon travelled, the universe expanded. The space between the photon and us stretched. So by the time that photon finally arrives at our telescopes, the original location from which it was emitted, if we could somehow mark it and track it, would now be an incredible 46.5 billion light-years away from us. This is why the observable universe is so much larger than 13.8 billion light-years. It's not just the distance light travelled, it's the distance that light's starting point is now from us, due to the continuous expansion of space over cosmic history. This boundary, this cosmic horizon, is what we call the quote 9. It represents the maximum distance from which particles could have travelled to the observer in the age of the universe. Anything beyond that horizon, any light emitted from a source further away, simply hasn't had enough time to reach us yet, or the space between us, and it has expanded so much that its light will never reach us. This concept leads us to the very edge of our observable universe, the cosmic microwave background, or CMB. The CMB is often described as the afterglow of the Big Bang. For the first 380,000 years after the Big Bang, the universe was an incredibly hot, dense plasma, a thick, opaque fog of charged particles, protons, electrons, and photons, constantly scattering off each other. Photons couldn't travel freely through this plasma. They were constantly bumping into electrons, making the universe effectively opaque, like being inside a star. But as the universe expanded, it cooled. When it cooled to about 3000 Kelvin, around 2700 degrees Celsius, something momentous happened. Electrons and protons were finally able to combine and form stable, neutral hydrogen atoms. This event is called recombination. Suddenly, with the free electrons now bound into atoms, the photons were no longer constantly scattering. The universe became transparent. This first light that was finally free to travel, the light released at the moment the universe became transparent, is what we detect today as the cosmic microwave background. When we observe the CMB, we are literally looking back in time to when the universe was only 380, 00 years old. It's like looking at the one, quote 11. The last moment these photons interacted with matter before streaming freely across the cosmos. This light has been travelling for 13.8 billion years, and due to the expansion of space, the region of space where that light was emitted is now about 46.5 billion light-years away. The CMB is incredibly uniform, almost perfectly smooth, telling us that the early universe was remarkably homogeneous, but there are tiny, subtle temperature fluctuations in the CMB, variations of just a few parts in 100,000. These minuscule differences are incredibly important because they represent the seeds of all structure in the universe, the initial density variations that, over billions of years, grew through gravity to form galaxies, clusters of galaxies, and the vast cosmic web we see today. So, when you look up at the night sky, you're not just seeing stars and galaxies in their current state. You're looking back in time, and the very furthest thing you can see, the ultimate limit of our observable universe, is this faint ancient glow of the cosmic microwave background, a relic from the universe's infancy. So, we've established that the observable universe is a vast, ever-expanding sphere, a bubble of existence limited by the speed of light and the age of the cosmos, with its true size inflated by the stretching of space itself. The CMB marks the furthest boundary of what we can ever hope to see, a snapshot of the universe when it was a mere infant. But here's the crucial point. The observable universe is just that. Observable. It's our horizon, not necessarily the edge of reality. What lies beyond this 46.5 billion light-year boundary? What's out there that light simply hasn't had time to reach us from yet? Or, even more profoundly, what if the entire universe is fundamentally much, much larger than our observable bubble, perhaps even infinite. That question about the true scale and nature of the cosmos beyond our current sight is where our journey truly begins, as we venture into the realm of the unobservable universe and the mind-bending possibilities it holds. So, we've peered right to the very edge of what's knowable, the ultimate horizon of our observable universe, a vast cosmic bubble stretching 46.5 billion light-years in every direction. We've seen the faint afterglow of creation, the cosmic microwave background, and understood that everything within that sphere began as tiny fluctuations in that ancient, hot plasma. But the question that truly keeps me up at night, the one that makes the hairs on my arms stand up, is this: what lies beyond? Is our observable universe simply a tiny speck within an infinitely larger cosmos? Or is the entire universe finite yet unbounded, like the surface of a sphere, just so vast that we can only ever see a small patch of it? This isn't just a philosophical musing, it's one of the most profound scientific mysteries of our time, and it challenges our very understanding of reality. Let's be clear, when we talk about the Kriya Quote 12, we're talking about the part of the universe from which light has had time to reach us. It's a sphere centered on us, wherever we happen to be. If you were billions of light years away, your observable universe would be centered on you, and it would overlap with ours, but also include regions we can't see. Think about it like standing in a vast ancient forest. You can only see so far in any direction before the trees block your view. That's your observable forest. But the forest itself could stretch for thousands of miles beyond your line of sight, or it could be infinite. The trees don't suddenly stop just because you can't see them anymore. The universe is the same way. The fact that we can't see beyond our cosmic horizon doesn't mean there's nothing there. It just means the light from whatever is there hasn't had enough time to reach us, or the space between us has expanded so rapidly that the light has been stretched beyond detectability, or perhaps even beyond our horizon altogether. So, how do we even begin to ponder the unseeable? We turn to theory, to the elegant equations of general relativity, and to the subtle clues imprinted on the universe itself. One of the most critical clues comes from the overall shape or geometry of the universe. Imagine our universe as a giant three-dimensional surface. What kind of surface is it? Einstein's general relativity tells us that the geometry of space is intimately linked to the amount of matter and energy within it. There are three main possibilities. 1. A closed universe. This would be like the surface of a sphere. If you walked in a straight line long enough, you'd eventually come back to where you started. In a closed universe, space itself has positive curvature, like the surface of a ball. It would be finite in size but have no edge. If our universe were closed, we might, in principle, eventually see light from distant galaxies that has travelled all the way around the universe to reach us. Think of it like looking at the back of your head in a funhouse mirror. If the mirror was the entire universe. 2. An open universe. This would be like the surface of a saddle or a Pringle chip. It has negative curvature, and if you travelled in a straight line, you would never come back to your starting point. An open universe would be infinite in extent. 3. A flat universe. This is like a perfectly flat sheet of paper. It has zero curvature, and like an open universe, it would be infinite in extent. If you travelled in a straight line, you'd never return. Which one is it? For decades, cosmologists have been trying to measure the universe's curvature, and the answer, based on incredibly precise measurements of the cosmic microwave background, CMB, that ancient baby picture of the universe we talked about, is astonishingly clear. Our universe appears to be flat. Not just a little bit flat, but remarkably flat. This flatness is determined by comparing the actual density of matter and energy in the universe to a theoretical. Quote Just 15. If the universe's density is greater than the critical density, it's closed. If it's less, it's open. If it's exactly equal, it's flat. And our measurements, particularly from the WMAP and Planck satellites, tell us that the universe's density is incredibly close to this critical value. Why is this so mind-blowing? Because a truly flat universe implies that it is infinite. Yes, you heard that right. An infinite universe. Think about that for a moment. If the universe is truly infinite, then not only is there no edge beyond our observable horizon, but there is an endless expanse of space, filled with an endless number of galaxies, stars, and planets, stretching on forever. But wait, how can something be infinite if it also had a beginning? The Big Bang. This is where our understanding gets truly fascinating. The Big Bang wasn't an explosion in space, but an expansion of space itself. If the universe was already infinite at the moment of the Big Bang, then it has remained infinite ever since. It simply expanded from an infinitely dense, infinitely hot state to an infinitely less dense, infinitely cooler state. The infinity just got bigger, if that makes any sense. However, there's a huge caveat here. While the universe appears flat on the scales we can observe, we can't definitively say it's truly infinite. Our measurements only tell us that the universe is flat within the observable horizon. It could still be a closed universe, but one so incredibly vast that its curvature is undetectable to us. Imagine an ant on a gigantic beach ball. To the ant, its immediate surroundings would appear perfectly flat, even though it's on a curved surface. Our observable universe might be that tiny patch on a much, much larger, gently curving cosmic sphere. This brings us to one of the most revolutionary ideas in cosmology, one that helps explain why the universe is so flat and why the CMB is so uniform. Cosmic inflation. Let's rewind to the very beginning, just a tiny fraction of a second after the Big Bang. The universe was incredibly hot and dense, but also incredibly tiny. For a fleeting moment, an almost incomprehensibly brief period, something extraordinary happened. The universe didn't just expand, it underwent an exponential, super-fast growth spurt. We're talking about a period where the universe expanded by a factor of at least 1026, that's a 1 followed by 26 zeros, in less than a trillionth of a second. Imagine blowing up a tiny balloon to the size of the entire observable universe in an instant. That's inflation. Why do we believe in inflation? Because it elegantly solves several major puzzles that the standard Big Bang model couldn't explain. 1. The flatness problem. If the universe wasn't perfectly flat at the beginning, its curvature would have rapidly grown more extreme over time. Yet, we observe it to be flat. Inflation is like taking a tiny wrinkled piece of paper and stretching it out to an enormous size. Any initial wrinkles or curves would be smoothed out, making the paper appear incredibly flat. So, inflation naturally flattens the universe. 2. The horizon problem. When we look at the cosmic microwave background, we see that different regions of the sky, which are so far apart that light hasn't had time to travel between them since the Big Bang, have almost exactly the same temperature. How could they be so uniform if they've never been in communication? Inflation solves this by proposing that these regions were in causal contact before inflation. They were once incredibly close together, reached thermal equilibrium, and then inflation stretched them apart so rapidly that they now appear causally disconnected. 3. The monopole problem. This is a bit more technical, but inflation also explains the absence of certain exotic high-energy particles, magnetic monopoles, that the standard Big Bang model predicts should exist in abundance. So inflation isn't just a quirky idea. It's a powerful framework that accounts for some of the most puzzling observations about our universe. But here's the kicker, the truly mind-bending implication of inflation. If inflation happened, then the entire universe is almost certainly far, far larger than our observable universe. Think about that balloon analogy again. Our observable universe is just one tiny, tiny patch on that incredibly stretched out surface. The part of the universe that underwent inflation and continued expanding is gargantuan, potentially infinitely larger than what we can ever hope to see. We are, in essence, inside a tiny bubble of space-time, and beyond our horizon lies an unimaginable expanse of more space-time, filled with more galaxies, more clusters, more cosmic structures, identical in nature to what we see, but forever beyond our direct observation. This isn't just... Quote 18. This is the idea that the universe we inhabit, the one we call... Quote 19, might be just a small fraction of a much grander, truly immense cosmos. We're talking about a scale that defies human intuition. If the observable universe has a radius of 46.5 billion light-years, the entire universe, according to inflationary models, could be so large that its size is beyond comprehension. A number so big it has more digits than there are particles in our observable universe. Some estimates suggest it could be at least 10,023 times larger than the observable universe, and potentially truly infinite. So, when we ask what's beyond our observable universe, the most scientifically supported answer, stemming from the implications of cosmic inflation and the observed flatness of space, is more universe. A lot more. An unimaginably vast, perhaps infinite amount of universe, likely governed by the same physical laws and filled with the same kinds of cosmic structures we see. Galaxies, nebulae, black holes, everything we're familiar with, just stretching on and on, forever out of our sight. This perspective is humbling, isn't it? It means that everything we've ever studied, everything we've ever discovered, all the galaxies we've catalogued, the planets we've found, the life we search for, it's all contained within a tiny, finite bubble of the cosmos. The rest of it, the truly vast majority, remains a mystery, a realm of endless possibilities, forever beyond our direct reach. But what if it's not just? Quote 20. What if the conditions, the very laws of physics, change beyond our horizon? What if other, quote 21, of space-time separate universes exist out there? That, my friends, is the tantalizing leap into the realm of the multiverse, a concept even more mind-bending than an infinite universe, and that's a journey we'll embark on next. For now, let's just sit with the profound realization that our cosmic home is likely just a tiny, precious island in an ocean of unimaginable scale. We left off with a truly mind-boggling thought. If the universe is flat, and therefore potentially infinite, our observable bubble is just a tiny, insignificant speck within an unimaginably vast cosmic ocean. And here's the kicker. That ocean might not be uniform. The laws of physics, the very constants that govern our reality, might not be the same everywhere. This isn't just a wild guess. It's a logical, albeit speculative, extension of the very theories we discussed, especially cosmic inflation. So, if our observable universe is just one tiny patch in a much larger, perhaps infinite cosmos, what else could be out there? This question opens the door to one of the most profound and hotly debated concepts in modern cosmology, the multiverse. Now, when we talk about the multiverse, we're not just talking about some sci-fi fantasy. We're talking about a spectrum of theoretical possibilities, each built upon different scientific foundations, each more mind-bending than the last. Let's dive in and explore these different, quote, 22 of the multiverse. The Level 1 multiverse, infinite parallel universes. Imagine our entire flat, infinite universe. If it truly stretches on forever, then by definition, everything that can possibly happen will happen an infinite number of times. Think about it this way. The amount of matter and energy within a given volume, say, a sphere the size of our observable universe, is finite. There are also a finite number of ways to arrange that matter and energy within that volume, even if that number is astronomically large. But if space is infinite, and it's filled with these finite arrangements, then eventually, statistically, these arrangements must repeat. Somewhere out there, an unimaginable distance away, there could be another observable universe identical to ours, and another, and another. It's like shuffling a deck of cards. There's a finite number of possible arrangements, but if you shuffle it enough times, you'll eventually repeat a sequence. Or consider an infinite number of monkeys eventually typing out the complete works of Shakespeare. In an infinite universe, every possible arrangement of particles that can exist in a volume the size of our observable universe must eventually exist, and not just once, but an infinite number of times. This means that somewhere, unfathomably far away, there's another you reading this exact text, living an identical life, and another you who made a slightly different choice this morning, and another you who is a spacefaring explorer. These aren't alternate realities in a mystical sense. They are simply spatial repetitions within the same infinitely vast universe. They are governed by the same laws of physics we know and love, but because they are so incredibly far away, they are forever beyond our ability to observe or interact with them. The sheer scale makes it impossible. This Level 1 multiverse is the most straightforward implication of an infinite universe. It's not about different physical laws, but about the sheer statistical inevitability of repetition in an endless expanse. It simply extends what we observe locally to a global infinite scale. The Level 2 multiverse, bubble universes and eternal inflation. Now, let's turn up the dial on the weirdness. Remember cosmic inflation, that incredibly rapid exponential expansion that smoothed out the early universe and stretched it flat? What if inflation didn't just happen once, and then stop everywhere? What if it's still happening somewhere? This brings us to the concept of eternal inflation. Imagine inflation as a vast overarching process, like a boiling pot of water, bubbles of Jnana, quote 26, space-time, like our own universe, spontaneously form when inflation temporarily stops in a particular region. These bubbles then expand and cool, eventually forming galaxies, stars, and planets. But in the surrounding, quote 27, the inflating space-time, the process of inflation continues, eternally spawning new bubbles. Think of it as an endless cosmic foam, where each bubble is a brand new universe. Our observable universe is just one tiny, tiny part of one such bubble. The truly mind-bending part of eternal inflation is that each of these, quote 28, could have different initial conditions. Tiny quantum fluctuations during inflation could lead to different fundamental constants, different particle masses, even different numbers of spatial dimensions or entirely different laws of physics. This is where the hint from Chapter 2 really comes into play. Beyond our observable horizon, in a different bubble universe, gravity might be stronger, the speed of light might be different, or there might be completely new forces at play. Carbon atoms, as we know them, might not even exist. The very fabric of reality could be woven from different threads. These bubble universes are not merely spatially separated like the Level 1 multiverse. They are causally disconnected from each other. The space between them is still inflating so rapidly that even light cannot travel from one bubble to another. They are forever beyond our reach, beyond our sight, beyond any possible interaction. We are trapped within our own cosmic bubble, completely unaware of the countless others that might exist, each with its own unique set of rules. This Level 2 multiverse elegantly addresses a profound cosmic mystery, the Yas fine-tuning problem. Why are the physical constants of our universe, like the strength of gravity, the mass of an electron, the cosmological constant, so perfectly tuned for the emergence of life? If they were even slightly different, stars wouldn't form, atoms wouldn't be stable, or life as we know it would be impossible. If there are an infinite number of bubble universes, each with slightly different physical laws, then it's no surprise that we find ourselves in one that can support life. We simply couldn't exist in any of the others. It's a cosmic lottery, and we won. The Level 3 multiverse, the many worlds of quantum mechanics. Let's take a slight detour from cosmology and dip our toes into the perplexing world of quantum mechanics. At the subatomic level, particles don't have definite states until they are observed. They exist in a superposition of all possible states simultaneously. It's only when we measure them that their wave function, quote 29, into a single, definite outcome. But what if the wave function never truly collapses? This is the core idea behind the many worlds interpretation, MW, of quantum mechanics, proposed by Hugh Everett III in 1957. In this view, every time a quantum measurement is made, or every time an interaction occurs that has multiple possible outcomes, the universe splits into multiple parallel universes. Each universe represents a different possible outcome, and all of them are equally real. Imagine Schrödinger's famous cat experiment. In the MWI, when the Geiger counter either fires or doesn't, the universe doesn't choose one outcome. Instead, it branches. In one universe, the cat is alive. In another, it's dead. And we, the observers, are also split. experiencing one outcome in one branch and the other outcome in another. This isn't about different spatial locations or separate bubbles. It's about an infinite number of universes constantly branching and diverging, creating an ever-growing tree of possibilities. Every decision you make, every photon that hits your eye, every quantum event in the cosmos potentially creates new branches of reality. The an quote 30 an in this level 3 multiverse isn't just a distant spatial copy. It's a version of you that split off at some point in the past, living out a different set of choices and quantum outcomes. This is perhaps the most difficult multiverse concept to intuitively grasp, as it suggests an infinite number of quote 31 constantly being created. The level 4 multiverse, mathematical universes. Finally, we arrive at the most abstract and philosophical level of the multiverse, proposed by cosmologist Max Tegmark. This idea suggests that every mathematically consistent structure corresponds to a real, existing universe. Think about it. Our universe is governed by a specific set of mathematical laws and constants. It's a particular mathematical structure, but couldn't there be other mathematically consistent structures? Structures where the fundamental numbers are different, where the rules of logic themselves are slightly altered, or where entirely different mathematical frameworks apply. In this level 4 multiverse, these alternative mathematical structures aren't just abstract concepts, they are other universes. Our universe is simply one manifestation of a particular mathematical framework. Other universes could exist where the laws of physics are entirely different mathematical equations, perhaps even ones we haven't yet conceived. This level pushes the boundaries of what we typically consider. Quote 33. It suggests that reality itself is fundamentally mathematical, and if a mathematical structure can be consistently described, then it exists as a universe. It's the ultimate expression of the idea that anything mathematically possible is physically real. Why all this talk of multiverses? The anthropic principle revisited. These multiverse hypotheses, especially levels 1 and 2, offer compelling answers to some of cosmology's deepest questions, particularly the fine-tuning problem we touched on. If there's only one universe, then the exquisite fine-tuning of its constants for life seems like an incredible coincidence, almost requiring some sort of designer. But if there are countless universes, each with different properties, as in level 2, then it's no longer a coincidence. It's an inevitable outcome of probability. We are here to observe a universe that supports life because we couldn't be in one that didn't. This is the weak anthropic principle. It's not that the universe was designed for us. It's that we are simply in one of the universes that allows for our existence. If there are enough cosmic lottery tickets, someone is bound to win the jackpot. The grand unknowable tapestry. It's important to stress that these multiverse theories, particularly levels 2, 3, and 4, are highly speculative. We currently have no direct empirical evidence for them. We can't see beyond our observable horizon, let alone peer into other bubble universes or quantum branches. However, they are not baseless fantasies. They are logical, often elegant extensions of our most successful scientific theories: general relativity, cosmic inflation, and quantum mechanics. They are an attempt to explain profound observations about our universe that otherwise remain mysterious. The idea that our universe, as vast and ancient as it is, might just be one tiny thread in an unimaginably grander tapestry of existence is both humbling and exhilarating. It challenges our fundamental understanding of reality and our place within it. What lies beyond the observable universe, then? Perhaps an infinite expanse of more of the same, perhaps a foam of other universes with different laws, perhaps an ever-branching tree of quantum possibilities, or perhaps even the instantiation of every mathematically consistent reality. The journey into the cosmos is truly an exploration into the limits of human imagination and the profound depths of scientific inquiry. We stand at the precipice of understanding, gazing out at possibilities that stretch far beyond the light we can see, into realms where reality itself takes on forms we can barely conceive. And that, my friends, is what makes the universe so endlessly captivating. It beckons us to keep questioning, to keep exploring, to keep dreaming of what's beyond. All right, buckle up, cosmic adventurers. We've journeyed through the infinite expanse of our universe, peered into the myriad possibilities of the multiverse, and even flirted with the mind-bending concept that reality itself might be a mathematical construct. If that last bit, the level 4 multiverse, made your brain feel like a quantum-entangled pretzel, you're not alone. It pushes the very limits of what we can imagine, let alone comprehend. But what if the RISE Quote 34s isn't just more universes, or different universes, but a fundamentally different structure to reality itself? What if the universe, or the multiverse, isn't just bigger, but richer in ways we can barely perceive? Today, we're going to dive headfirst into a concept that sounds like pure science fiction, yet is a cornerstone of some of our most promising attempts to unify the fundamental forces of nature, higher dimensions. Yes, I'm talking about dimensions beyond the familiar 3 spatial dimensions, length, width, and height, that define our everyday existence, plus the one dimension of time that relentlessly pulls us forward. What if there are more? What if our reality is just a tiny slice of a much grander, multi-dimensional tapestry? Think about it with me for a moment. We're 3-dimensional beings, right? We move forward, backward, left, right, up, and down. Our universe, as we experience it, feels incredibly solid and real in these 3 dimensions. But imagine, if you can, a hypothetical 2-dimensional being. Let's call her Flatland Alice. Alice lives on a perfectly flat surface, a cosmic sheet of paper. She can move forward, backward, left, and right. But she has absolutely no concept of up or down. Her entire reality is confined to that flat plane. Now, if we were to look down at Flatland Alice's world, we'd see her entire existence laid out before us. We could even reach down and lift her off her plane, an experience that would be utterly bewildering and terrifying to her. From her perspective, she'd suddenly vanish from her world, only to reappear somewhere else, with no understanding of the up and down dimension that allowed her to be moved. To her, it would be magic or perhaps a godlike intervention. This is because she's fundamentally limited by her 2D perception. Now flip that perspective. What if we are like Flatland Alice, but in 3 dimensions? What if there's a 4th spatial dimension, or a 5th, or even more, that we simply can't perceive or move through? Imagine a being from a higher dimension observing us. They might see our entire past, present, and future laid out before them, much like we see Flatland Alice's entire life on her 2D plane. They could reach into our world, seemingly appearing and disappearing at will, performing feats that would strike us as miraculous, simply because they're operating in dimensions we don't have access to. This isn't just a fun thought experiment, my friends. This is a serious area of theoretical physics, deeply embedded in some of our most ambitious attempts to reconcile the fundamental forces of nature. For decades, physicists have wrestled with a profound cosmic imbalance, the incredible weakness of gravity compared to the other fundamental forces, electromagnetism, and the strong and weak nuclear forces. Think about it. A tiny magnet can pick up a paperclip, effortlessly overcoming the gravitational pull of an entire planet. Why is gravity so incredibly feeble? One of the earliest and most elegant attempts to incorporate extra dimensions came in the 1920s with the work of Theodor Kaluza and Oscar Klein. They were trying to unify Albert Einstein's theory of general relativity, which describes gravity, with James Clerk Maxwell's theory of electromagnetism. Kaluza had this brilliant, almost audacious idea. What if the universe actually has 5 dimensions? Our familiar 4, 3 spatial, 1 temporal, plus 1 extra spatial dimension. When Klein later refined Kaluza's theory, he proposed that this extra dimension isn't large like our visible dimensions, but rather curled up on itself, incredibly tiny, like a microscopic loop at every point in space. Picture a garden hose. From a distance, it looks like a one-dimensional line. An ant crawling along its length can only go forward or backward. But if you get up close, you realize the hose also has a circumference, a small curled-up second dimension that the ant can walk around. Kaluza and Klein suggested that our extra dimension is like that, so incredibly small, so tightly compactified, that we simply can't perceive it or move through it with our macroscopic bodies. Yet, its presence, they theorized, could manifest as the electromagnetic force in our familiar 4D world, while gravity operated in all 5 dimensions. It was a beautiful, albeit incomplete unification. Fast forward to today, and the concept of extra dimensions has become absolutely central to our leading candidate for a theory of everything, string theory, and its successor, M-theory. These theories propose that the fundamental building blocks of the universe aren't point-like particles, but tiny, vibrating, one-dimensional strings. The different vibrational modes of these strings give rise to all the different particles and forces we observe, including gravity. But here's the kicker, and this is where it gets truly mind-bending. For string theory to be mathematically consistent, for its equations to work out without leading to absurdities, it requires a universe with more than 4 dimensions, a lot more. The original bosonic string theory needed 26 dimensions. Superstring theories, which incorporate fermions, matter particles, and bosons, force-carrying particles, typically require 10 dimensions, 9 spatial and 1 time. And M-theory, which is thought to be the overarching framework unifying the 5 different superstring theories, postulates 11 dimensions. 11 dimensions. Can you even imagine that? We struggle with 4 spatial dimensions, let alone 10 or 11. So if these extra dimensions exist, where are they? Why don't we see them? Why don't we experience them? The prevailing idea, much like in Kaluza-Klein theory, is that these extra dimensions are also compactified, or curled up, into incredibly tiny, intricate shapes at every point in our familiar 3-dimensional space. These shapes, known as Calabi-Yau manifolds, are incredibly complex multi-dimensional geometries far too small for us to ever directly detect. They determine the specific properties of the particles and forces we observe, essentially tuning our universe. Think of it like the specific way a string vibrates, producing a certain musical note. The shape of the curled-up dimension determines the note of our universe's physics. But there's another fascinating possibility, one that could elegantly explain gravity's weakness: the large extra dimensions or brain world models. In these scenarios, our entire observable universe, everything we see and touch and are, is essentially a three-dimensional brain, short for membrane, floating within a higher dimensional bulk space. Imagine a piece of paper, our brain, floating in a bathtub, the bulk. The water fills the whole tub, but the paper only exists on its 2D surface. In brain world theories, most of the fundamental forces, electromagnetism, the strong and weak nuclear forces, are confined to our brain. They can't leak off into the extra dimensions. But gravity, being a property of space-time itself, is different. It can propagate into the higher dimensional bulk. So when we feel gravity, we're only experiencing a fraction of its true strength. Most of its power is diluted or leaks away into these extra dimensions, making it appear incredibly weak to us on our brain. This could be why a small magnet can defy the gravity of an entire planet. The magnet's electromagnetic force is fully contained within our brain, while Earth's gravitational pull is spread out across the bulk. This idea opens up some truly mind-boggling implications. If our universe is just one brain in a multi-dimensional bulk, could there be other brains out there? Other universes, perhaps with different physical laws, existing parallel to ours, just a millimeter in a higher dimension away, yet entirely invisible and inaccessible to us. This takes the Level 2 multiverse concept, bubble universes, and gives it a whole new spatial context, suggesting they might not be infinitely far away in our dimensions, but just a sideways step away in another dimension. Could these other brains occasionally collide or interact, causing cosmic events that we misinterpret? Some theories even suggest that the Big Bang itself might have been the result of two brains colliding. Imagine that. The birth of our entire universe, not from a singular point in nothingness, but from a cosmic fender-bender in a higher dimensional realm. The search for evidence of these extra dimensions is one of the most exciting frontiers in physics. Particle accelerators like the Large Hadron Collider, LHC, are constantly pushing the boundaries of energy, looking for signs that particles might be disappearing into extra dimensions, or for new particles that could only exist if extra dimensions were real. If a particle could escape our brain into the bulk, it would appear to us as a loss of energy, a missing piece in our calculations. So far we haven't found definitive proof, but the search continues, fueled by the profound implications. And what if these dimensions aren't just spatial? What if there are other temporal dimensions, or even entirely different types of dimensions we can't even conceive of? The possibilities are truly endless, and they challenge our most fundamental assumptions about reality. We're so accustomed to our 3+1 dimensional existence that it's hard to imagine anything else. But just as Flatland Alice couldn't comprehend up, we might be blind to the vast unseen fabric that truly constitutes our universe. So, as we contemplate what lies beyond the observable universe, we're not just thinking about more galaxies, or even more universes. We're venturing into the very architecture of reality itself. We're asking if the stage upon which all of existence plays out is far grander, far more complex, and infinitely more intricate than our limited senses can currently grasp. It's a journey not just to the edges of space, but to the very core of what it means to exist within this magnificent, multi-dimensional cosmos. Welcome back, cosmic voyagers. We've journeyed through the mind-bending realms of infinite parallel universes, bubble multiverses, and the tantalizing possibility of extra-spatial dimensions where gravity itself might be a fleeting visitor. We pondered if our entire universe is just a three-dimensional, quote, 35, floating in a higher dimensional, quote, 36 to space, with other brain universes potentially existing parallel to ours, just out of reach. But what if the very nature of our reality, even within our own universe, is fundamentally different from what we perceive? What if our three-dimensional existence, with all its depth and complexity, is actually just a projection? This isn't science fiction, my friends. This is the holographic principle. One of the most profound and challenging ideas in modern theoretical physics, and it takes our exploration of what's beyond to an entirely new level. Think about a hologram, that flat two-dimensional image that, when lit correctly, appears to pop out into a full three-dimensional scene. You can walk around it, see different perspectives, and it truly looks like a solid object, yet all the information defining that 3D image is encoded on a 2D surface. Now, imagine if our entire universe worked like that. The genesis of the holographic principle lies in the enigmatic world of black holes. For decades, physicists grappled with what happens to information when something falls into a black hole. According to classical physics, information should be preserved, but Stephen Hawking's discovery that black holes emit radiation, Hawking radiation, and eventually evaporate seemed to suggest that any information swallowed by a black hole would be lost forever. This posed a serious challenge to the fundamental laws of quantum mechanics, leading to what's known as the black hole information paradox. Enter Jacob Bekenstein, who proposed that black holes possess entropy, a measure of disorder or, crucially, information. What's truly astonishing about Bekenstein's work, later refined by Hawking, is that a black hole's entropy isn't proportional to its volume, as you might expect for a three-dimensional object. Instead, it's proportional to its surface area, specifically the area of its event horizon, the point of no return. Pause and let that sink in. For any ordinary object, the amount of information it contains scales with its volume. A bigger box holds more stuff. But for a black hole, the ultimate container of matter and energy, the maximum amount of information it can hold is encoded on its two-dimensional boundary. This was a radical departure from conventional thinking. This insight sparked a revolution. In the early 1990s, Leonard Susskind and Gerard 't Hooft formalized this concept into the holographic principle. It suggests that the description of a volume of space can be thought of as encoded on a lower dimensional boundary, or surface of that region. In simpler terms, all the information needed to describe everything happening in our three-dimensional universe might be entirely contained on a distant two-dimensional surface. So, if our universe is a hologram, what does that mean for us, the perceived inhabitants of this 3D projection? It means that our everyday experience of depth, space, and even time could be an elaborate illusion. a sophisticated rendering of information stored on a boundary we can't directly perceive. It's like living inside a video game, where the game world feels utterly real and three-dimensional to the character, but all the data that creates it is actually stored on a flat hard drive. Now, where could this holographic screen or boundary be? One popular idea, particularly in the context of our observable universe, is that the information describing everything inside our cosmic bubble is somehow encoded on its distant edge, perhaps the cosmic microwave background itself, or an even more distant theoretical boundary. It sounds wild, doesn't it? But it's a serious area of research, particularly within the framework of string theory. In fact, one of the most compelling pieces of evidence for the holographic principle comes from string theory. The ARDS-CFT correspondence. This monumental theoretical breakthrough proposed by Juan Maldacena suggests a profound duality between two seemingly unrelated types of theories. 1. Anti-de Sitter, ADS, space. A specific type of negatively curved space-time, think of a saddle shape, that includes gravity, often described by string theory. This is our bulk, or higher dimensional space. 2. Conformal field theory, CFT. A quantum field theory that lacks gravity and lives on the boundary of the AD space, in one fewer dimension. The AD-CFT correspondence states that these two theories, one with gravity in higher dimensions and one without gravity in lower dimensions, are mathematically equivalent. They are different descriptions of the exact same physics. This means a universe with gravity in 3 + 1 dimensions, 3 spatial dimensions plus 1 time dimension, could be perfectly described by a quantum field theory without gravity, living on its 2 + 1 dimensional boundary. This isn't just a mathematical curiosity, it's a concrete realization of the holographic principle. It tells us that what we perceive as a universe with gravity and all its complexities might be nothing more than a projection from a simpler, gravity-free system existing on a distant lower dimensional surface. The implications are staggering. It suggests that gravity itself, and perhaps even the very fabric of space-time, might not be fundamental, but rather an emergent phenomenon arising from the entanglement of quantum information on a holographic screen. So what does this mean for what's beyond the observable universe? If our universe is a hologram, then the beyond isn't just more space, or even other dimensions. It's the source of the projection. It's the quote 45 or the quote 46 that creates our reality. This could be a realm where fundamental laws are different, where concepts like space and time as we know them don't even exist. It could be a purely informational realm, an abstract mathematical structure that gives rise to our physical reality. And if our universe is a hologram, could there be other holograms? Could the bulk space from our brain world models be the canvas for multiple holographic projections, each giving rise to its own universe? The holographic principle doesn't directly imply a multiverse, but it certainly opens up new avenues for thinking about the fundamental nature of reality that could support such ideas. If our reality is just information, then the possibilities for different informational constructs are endless. Some physicists even take this idea a step further, proposing the digital universe hypothesis, or the simulation hypothesis. If reality is fundamentally informational, and if all that information can be encoded and processed, then it's not a huge leap to wonder if our universe is in fact a sophisticated simulation running on some incomprehensibly powerful computer. This is a highly speculative idea, often debated in philosophical circles, but it stems from the same deep questions about information and reality that the holographic principle addresses. If we are a hologram, who or what is the projector? Of course, the holographic principle is still a theoretical framework, and directly testing it is incredibly challenging. How do you find evidence that your 3D reality is actually a 2D projection? Some researchers are looking for subtle pixelation or graininess in space-time at incredibly small scales, the quantum equivalent of seeing the individual dots that make up a holographic image. Experiments involving gravitational waves and cosmic ray observations are also being scrutinized for any anomalies that might hint at a holographic universe. For now, the holographic principle offers us a breathtaking new perspective on reality. It challenges our most basic assumptions about space, time, and matter. It suggests that the beyond isn't just a distant place, but potentially the very foundation upon which our reality is built. It reminds us that our universe, in all its perceived solidity and vastness, might be far more ephemeral and information-rich than we ever imagined. It's a journey into the nature of existence itself, pushing the boundaries of what we can even conceive, and as we continue to probe these profound mysteries, we realize that the universe, in its boundless strangeness, always has another layer to peel back, another illusion to shatter. What a time to be alive, to witness the unraveling of such cosmic secrets. We've journeyed through the infinite expanse of Level 1 multiverses, navigated the bubbling chaos of Level 2, wrestled with the quantum paradoxes of Level 3, and even contemplated the elegant structures of Level 4 mathematical universes. We've stretched our minds into higher dimensions, where gravity might leak away and entire universes could exist on parallel branes. And then we peered into the profound depths of the holographic principle. The unsettling idea that our entire three-dimensional reality might be nothing more than a projection from a lower dimensional surface, a cosmic hologram. This leads us to the ultimate, most mind-bending question, one that often accompanies the holographic principle and the AD-CFT correspondence. Is our universe a simulation? Think about it. If our reality is a projection, and information is fundamental, then the leap to a simulated universe isn't as far-fetched as it first seems. What if the Quote 51 encoding our reality is, in fact, the operating system of an incredibly advanced cosmic computer? What if the main, Quote 52, isn't a higher dimension or another universe, but the very code that generates our existence, running on hardware we can't even begin to imagine? It's a concept that challenges everything we think we know about existence, free will, and the very nature of reality. If we are simulated beings, then who are the programmers? What are their motivations? Is there a Quote 53 from which our simulation springs? And are there layers upon layers of simulations like nested Russian dolls, each more fundamental than the last? While the simulation hypothesis remains firmly in the realm of speculation, it forces us to confront the limits of our perception and the possibility that our understanding of reality is incredibly incomplete. It pushes us to ask, if our universe is a projection or even a simulation, what does that imply about the very bedrock of existence? What is reality really made of? Before we venture further into the truly mind-bending philosophical implications, let's acknowledge the colossal unknowns right here in our cosmic backyard, because even within the confines of our observable universe, there are profound mysteries that scream for a beyond not necessarily in space, but in our understanding of fundamental physics. I'm talking, of course, about dark matter and dark energy. These aren't just minor anomalies. They represent an astonishing 95% of the universe's total mass energy content. We can't see them, we can't directly detect them, but their gravitational influence is undeniable. They are the invisible architects shaping the cosmos, and they are a glaring indictment of how little we truly comprehend. Let's start with dark matter. We've known about its effects for decades. Back in the 1930s, astronomer Fritz Zwicky observed that galaxies in the Coma cluster were moving far too fast to remain gravitationally bound by their visible matter alone. He proposed the existence of unseen quote, to account for the discrepancy. Later, Vera Rubin's groundbreaking work in the 1970s showed that stars in the outer regions of spiral galaxies orbit at roughly the same speed as stars closer to the center. This is like a merry-go-round where the horses on the outside are spinning just as fast as those in the middle. It defies Newtonian physics unless there's an invisible halo of mass surrounding the galaxy, providing extra gravitational pull. We now have overwhelming evidence from gravitational lensing, the cosmic microwave background, and the formation of large-scale structures that dark matter is real. It makes up about 27% of the universe. But here's the kicker. We have no idea what it is. It doesn't interact with light, electromagnetic forces, or even the strong nuclear force. It only seems to interact gravitationally. Is it made of exotic, undiscovered particles that only exist in the Weta quote 56 of our standard model of particle physics? Could it be tiny black holes? Or is it something even stranger? Perhaps a manifestation of extra dimensions, or a subtle modification of gravity itself at cosmic scales? The answers, whatever they are, lie beyond our current grasp, hinting at a hidden sector of reality. And then there's dark energy. This is arguably the biggest mystery in all of cosmology. In the late 1990s, observations of distant supernovae revealed something utterly astonishing. The expansion of the universe isn't slowing down as everyone expected. It's accelerating. Imagine throwing a ball into the air expecting it to slow down and fall back, only to watch it speed up and fly away into space. That's how surprising this discovery was. Dark energy is the name we've given to whatever is causing this acceleration. It behaves like a repulsive force, pushing space apart faster and faster. It accounts for a staggering 68% of the universe's total mass energy. Is it the Mach quote 57 of empty space itself, as predicted by quantum mechanics? If so, our theoretical calculations are off by an absurd factor of 10 to 120. That's a 1 followed by 120 zeros. The largest discrepancy between theory and observation in the history of science. Could it be a new dynamic energy field, sometimes called quintessence, permeating the cosmos? Or is it a sign that our understanding of gravity, Einstein's magnificent general relativity, needs to be fundamentally revised at the larger scales? Dark matter and dark energy are not just missing pieces of a puzzle. They are monumental question marks that point to a reality far richer and more complex than our current theories describe. They demand that we look. Quote 59. Our current paradigms, either for new particles, new forces, or even a new understanding of space-time itself. This quest for a deeper understanding of space-time brings us back to the very fabric of reality, especially if we consider the implications of the holographic principle. If space-time is emergent, as holography suggests, what is it emerging from? What lies beneath the smooth, continuous sheet of space-time described by general relativity? This is where the thorny problem of quantum gravity enters the picture. You see, we have two incredibly successful theories that describe the universe. General relativity, which explains gravity and the large-scale structure of the cosmos, and quantum mechanics, which describes the behavior of matter and energy at the smallest scales. Both are incredibly accurate within their respective domains, but they are fundamentally incompatible. General relativity paints a picture of smooth, continuous space-time, while quantum mechanics insists on a universe built from discrete, probabilistic packets. When you try to combine them, the math breaks down, giving us infinite nonsensical answers. It's like trying to fit a square peg into a round hole, only the peg and hole are both masterpieces in their own right. So, what happens at the Planck scale? The unimaginably tiny realm where gravity becomes as strong as the other fundamental forces, and quantum effects dominate space-time itself. At this scale, about 10⁻35 meters, billions of times smaller than an atom, space-time isn't smooth anymore. Many theories of quantum gravity suggest it becomes a frothing, bubbling quantum foam, a chaotic sea where space-time itself is constantly fluctuating, popping in and out of existence. One of the leading contenders for a theory of quantum gravity, alongside string theory, is loop quantum gravity, LQG. While string theory suggests fundamental reality is made of tiny vibrating strings in higher dimensions, LQG takes a different approach. It posits that space-time itself is quantized. Instead of being a continuous backdrop, space is woven from discrete fundamental quote 60 or quote 61 of space, much like a fabric is woven from individual threads. Time, too, is quantized, flowing in discrete quote 62. Imagine zooming into an image on your computer screen. From a distance it looks smooth and continuous, but zoom in close enough and you start to see the individual pixels, the discrete units that make up the whole. LQG suggests that space-time is like that. At the Planck scale, what we perceive as continuous space and time dissolves into a network of these quantum loops, called sh 63 and s 64. This is a profound shift in perspective. If space-time is truly emergent, built from these fundamental quantum bits, then the 65ds isn't just more space or other universes, it's the very underlying structure from which space and time arise. Gravity, in this view, isn't a force propagating through space-time. It's an emergent property of this quantum geometry, a manifestation of the way these loops and networks are connected. This idea that reality might be fundamentally discrete, built from tiny indivisible units, resonates strongly with the notion of information being fundamental. If space-time is quote 66, then each quote 67 could be thought of as carrying a bit of information. This brings us back to the audacious idea proposed by physicist John Wheeler, who coined the phrase quote 68. Wheeler suggested that every physical, quote 69, every particle, every field, even space-time itself, derives its existence from quote 70 of information, from yes-no answers to fundamental questions about the universe. If the universe is fundamentally informational, then the certain quote 70 could be a vast cosmic information network, a kind of universal quantum computer. Our reality, our particles, our forces, our very experience of space and time would then be the output, the generated display of this deeper informational substrate. This doesn't necessarily mean we're in a simulation in the conventional sense, but it does imply that information, not matter or energy, is the most fundamental building block of everything. And what about our consciousness? Could it be more than just a byproduct of complex biological machinery? If reality is informational at its core, and if the act of observation plays a crucial role in quantum mechanics, where a particle exists in a superposition of states until it's measured, could consciousness itself be an integral part of the universe's informational processing? This is where science blurs into philosophy, venturing into realms like panpsychism, the idea that consciousness, or proto-consciousness, is a fundamental property of the universe, present to some degree in all matter, or integrated information theory, which attempts to quantify consciousness based on how much information a system can integrate. These are highly speculative ideas, but they invite us to consider a quote 73 that includes our inner experience, suggesting that the subjective reality of consciousness might be intertwined with the objective reality of the cosmos in ways we're only just beginning to imagine. So when we ask what's beyond the observable universe, we're not just asking about more galaxies or other bubble universes. We're asking about the nature of infinity, the fabric of space-time, the fundamental constituents of reality, and even the role of consciousness itself. We're asking if our 3D, time-bound existence is merely a projection, a simulation, or an emergent phenomenon from a deeper, stranger, and infinitely more complex reality. The observable universe, vast as it is merely the tip of a cosmic iceberg. Beyond its horizon lies not just more space, but potentially different dimensions, different physical laws, different realities, and perhaps even a different fundamental nature of existence. We stand at the precipice of these profound mysteries, armed with our scientific tools and our boundless curiosity, ready to continue our journey into the unknown. The universe, in its infinite wisdom, continues to surprise, challenge, and inspire us, beckoning us to look further, to think deeper, and to never stop asking, what else is out there? What else is there to learn? We left off contemplating a truly mind-bending idea, that our reality, the very fabric of space-time itself, might not be fundamental at all. Instead, it could be emergent, a grand, intricate illusion woven from something even more basic. Information. John Wheeler's profound question, it from bit, suggests that the universe, at its deepest level, isn't made of tiny particles or invisible fields, but of yes-no answers, of choices, of pure abstract information. And this, my friends, brings us face to face with perhaps the most profound mystery of all, the role of consciousness in this cosmic equation. If space-time is a projection, if our universe is a sophisticated simulation, if reality is fundamentally informational, then what does that make us? Are we just complex arrangements of these fundamental bits, processing information without truly understanding it? Or is there something more? Is consciousness, that undeniable subjective experience of being you, an essential ingredient in the universe's recipe? Think about it. We've explored the observable universe, pondered infinite parallels, imagined bubble universes, plunged into higher dimensions, and even considered our reality as a holographic projection. Each step has chipped away at our preconceived notions, revealing a cosmos far stranger and more intricate than we ever imagined. But all these ideas, from the Big Bang to quantum gravity, ultimately rely on the existence of a reality that can be observed, can be measured, can be understood. And who is doing the observing, measuring, and understanding? We are. Consciousness is the lens through which the universe perceives itself. So, let's dive into this ultimate frontier, the nature of information, its relationship to consciousness, and what that implies for the very fabric of existence. First, we need to broaden our understanding of RAM, quote 76. It's not just data on a hard drive or words on a screen. In physics, information is deeply tied to entropy, the measure of disorder or randomness in a system. The second law of thermodynamics tells us that the total entropy of an isolated system can only increase over time, meaning information tends to get dispersed and lost into greater disorder. But here's the fascinating twist. Physicists like Rolf Landauer showed that there's a minimum amount of energy required to erase one bit of information. This isn't just a theoretical curiosity. It implies that information isn't an abstract concept floating in the ether. It's physical. It has a tangible connection to energy and matter. Every interaction in the universe, every particle collision, every photon emitted, every black hole evaporating, involves the processing and transformation of information. The universe, in a very real sense, is a giant, incredibly complex information processor. It's constantly calculating, constantly evolving its state based on previous states. If the universe is information, then its entire history is an unfolding computation. This brings us back to quantum mechanics and its enduring enigma, the measurement problem. Remember how quantum particles exist in a superposition of all possible states until they are observed? It's like a cosmic choose-your-own-adventure book, where all paths exist simultaneously until you turn the page and make a choice. But what constitutes an observation? Does it require a conscious mind, or simply an interaction with a macroscopic measuring device? For decades, physicists have debated this. Some argue that consciousness is necessary to collapse the wave function, suggesting a direct link between mind and reality. Others contend that any irreversible interaction with the environment is enough, removing the need for a conscious observer. But even if it's the latter, it still implies that information about the quantum state is being recorded and processed by the universe itself. But let's not shy away from the deeper implications. If reality is informational, and if consciousness is what interprets and experiences that information, then perhaps consciousness isn't just an accidental byproduct of complex brains. Perhaps it's something more fundamental. This is where we touch upon ideas like panpsychism, the notion that consciousness, or at least proto-consciousness, isn't just limited to humans or animals, but is an intrinsic property of the universe itself, present in some rudimentary form even at the most basic levels of reality. Imagine the universe not as a collection of inert particles, but as a vast interconnected network where every Quote 80 has a tiny spark of awareness, and our brains are merely highly complex orchestrators of these sparks, allowing for sophisticated subjective experience. Consider the implications if our reality is a simulation. If we are digital beings in a digital world, then our consciousness would be an emergent property of the simulation's code, a complex algorithm running on a cosmic supercomputer. But then, who programmed the supercomputer, and what is their reality like? The rabbit hole just keeps getting deeper. This line of thinking forces us to confront the hard problem of consciousness. How do physical processes in the brain give rise to subjective experience? Why does the firing of neurons feel like something? If the universe is information, and we are part of that universe, then our consciousness might be the universe experiencing itself. We are, in essence, the universe's eyes and ears, its sense of wonder and its capacity for self-reflection. Could our individual consciousnesses be localized? Quote 82, into a larger cosmic consciousness or informational field. Imagine the universe as an ocean of information. Each of us is a wave, a unique manifestation of that ocean, yet fundamentally connected to the whole. When we gain knowledge, when we have an insight, are we simply accessing a deeper layer of this universal information? When we feel a profound connection to the cosmos, are we tapping into a shared informational substrate? This isn't just abstract philosophy. It has profound implications for how we view our place in the cosmos. If consciousness is fundamental, if information is the bedrock of reality, then the universe isn't just a cold, indifferent machine. It's a dynamic, self-organizing system that, through us, becomes aware of itself. The anthropic principle often speaks of the universe being fine-tuned for life. Perhaps it's even more profoundly fine-tuned for consciousness, for the ability of existence to observe and reflect upon its own intricate beauty. So, what lies beyond the observable universe, beyond the multiverse, beyond higher dimensions, beyond the holographic principle, beyond emergent space-time? Perhaps the ultimate beyond is the very source of the information that constitutes reality. What defines those fundamental bits? What is the substrate upon which this cosmic computation runs? Is there a programmer or an ultimate ground of being from which all information, all consciousness, all existence springs? These questions push us to the very edge of scientific inquiry and into the realms of metaphysics and spirituality. Could the universe itself be a giant idea, a thought in a cosmic mind? Or is it a self-generating informational system, an infinitely complex fractal that creates and defines itself without external input? We've journeyed from our cosmic neighborhood to the very edge of what we can conceive. We've stretched our minds to embrace infinities, explored the possibility of other realities, and grappled with the idea that our own reality might be a projection or a simulation. And now we confront the deepest mystery of all, the nature of consciousness and its inextricable link to the fundamental fabric of the universe. The more we learn, the more we realize how much we don't know. The observable universe is just the beginning. The journey into what's beyond is a journey into the nature of reality itself, a quest that intertwines physics, philosophy, and the profound mystery of our own existence. And that, my friends, is the most exciting adventure of all. The cosmos continues to beckon. promising endless wonders to those brave enough to ask the biggest questions. All right, my friends, we've journeyed through the mind-bending landscapes of the multiverse, peered into the hidden dimensions, contemplated our holographic existence, and even dared to ask if our reality is a meticulously crafted simulation. We've wrestled with the profound mysteries of dark matter and dark energy, and glimpsed a universe where space-time itself might be an illusion, emerging from something more fundamental. And then we arrived at perhaps the most audacious idea of all, that consciousness isn't just a passenger in this cosmic drama, but potentially a fundamental player, a window into the very fabric of existence. If reality is, at its deepest level, information, and if our conscious experience is about processing and interpreting that information, then the lines truly begin to blur. What if our individual awareness isn't just a flicker in the vastness, but a resonant frequency, a unique node in a grander cosmic consciousness? This isn't just poetic musing, it's a profound thought experiment rooted in the implications of an informational universe. If, quote, is true, if reality arises from fundamental bits of information, then the act of observation, the processing of information that defines consciousness, takes on an entirely new significance. It suggests that our very ability to perceive and question might be an intrinsic, rather than accidental feature of the cosmos. And this, dear explorers, brings us to the ultimate. Quote 89. If there is a cosmic information field, a quote 90 from which all existence springs, then what is that source? What is the quote 90 buena behind the simulation, the architect of the mathematical structures, the wellspring of cosmic awareness? This is where science, as we know it, begins to merge with philosophy, and perhaps even a form of spiritual inquiry, not in a dogmatic sense, but in the purest sense of seeking ultimate truth. We are trying to peer beyond the canvas of reality to understand the artist, or perhaps to understand the nature of the canvas itself. Think about it this way. We've spent centuries dissecting the universe, cataloguing its particles, charting its galaxies, decoding its laws. We've discovered the elegance of general relativity, the strangeness of quantum mechanics. But what if these laws, these particles, this very space-time, are not the ultimate reality, but rather the interface of a deeper, more profound truth? What if they are the operating system, the code that runs our universe? If that's the case, then the programmer isn't necessarily a being with a beard and a lightning bolt. It could be something far more abstract, far more encompassing. It could be the ultimate metaphysics, the foundational principles from which all possible physics emerge. Imagine a cosmic library, not of books, but of every conceivable mathematical structure, every logically consistent set of physical laws. Our universe, with its specific constants, its unique forces, its particular arrangement of matter and energy, would be just one shelf in that infinite library. This resonates with the level 4 multiverse, the idea that every mathematically consistent structure corresponds to a real, existing universe. But now we're asking, who writes the library? Or rather, what is the fundamental principle that allows for such a library to exist? Is it a cosmic algorithm, an emergent property of infinite possibility, or something else entirely, something so utterly alien to our current comprehension that our language and concepts simply fail to grasp it. We are, in essence, trying to describe a concept that might exist outside of space-time, outside of causation as we understand it, outside of the very fabric of our reality. It's like a character in a computer game trying to comprehend the programmer sitting at the keyboard. The programmer exists in a completely different domain, operating under different rules, with different capabilities. Our universe, our reality, is the output of that deeper domain. Consider the fine-tuning problem once more. The universe's fundamental constants, the strength of gravity, the mass of an electron, the energy density of the vacuum, are exquisitely tuned for the emergence of complex structures and, eventually, life. Change them even slightly, and stars wouldn't form, atoms wouldn't hold together, or the universe would collapse in an instant. Scientists often explain this with the Level 2 multiverse, countless bubble universes, each with different laws, and we just happen to be in one that supports us. But what if the programmer is exploring these possibilities? What if the ground of being is a realm of pure potential, and our universe is a specific actualization of that potential? This brings a new dimension to our search for dark matter and dark energy, and our quest for quantum gravity. What if these profound mysteries, these glaring holes in our understanding, aren't just missing pieces of a puzzle, but clues to the nature of the simulation itself? Perhaps dark energy, with its mysterious accelerating expansion, is a subtle hint of the underlying code being updated, or a boundary condition of our cosmic program. Perhaps dark matter is an artifact of the simulation, a placeholder for something we can't yet directly interact with because it operates on a different layer of the cosmic architecture. And the search for quantum gravity, for a theory that unifies the very small with the very large, if space-time is emergent, if it arises from a quantum foam or discrete atoms of space, then the ultimate programmer isn't designing space-time itself, but the rules by which space-time emerges. It's a layer deeper, a level of abstraction that defines the very conditions for existence. The enormity of these ideas can feel overwhelming, can't it? We are pushing against the very limits of human perception and language. We're trying to describe something that might be inherently indescribable, using tools forged in a reality that might itself be a construct. It's like a fish trying to understand the concept of, quote, 98, or a two-dimensional being trying to conceptualize, quote, 19. Our brains, evolved to navigate a three-dimensional world over relatively short timescales, struggle to grasp concepts that transcend space, time, and even causality. But here's the wondrous part: the very act of asking these questions, of reaching for these answers, is what makes us unique. Our insatiable curiosity, our drive to understand the why, and the what's beyond, is itself a profound cosmic phenomenon. If consciousness is fundamental, then our journey of discovery is the universe trying to understand itself. We are the universe's way of looking back at its own complexity, its own beauty, its own profound truths. This journey, this intellectual quest, isn't just about accumulating facts. It's about expanding our minds, challenging our assumptions, and embracing the sheer, mind-boggling strangeness of reality. It's about recognizing that the universe is far, far grander than we could ever imagine, and that our current understanding is but a tiny ripple on an infinite ocean of possibility. So when we talk about the ultimate beyond, we're not necessarily talking about a place or even a thing. We're talking about the source of all places and all things. We're talking about the fundamental nature of existence, the wellspring of information, the ground of being from which everything, every particle, every galaxy, every thought, every conscious experience ultimately springs. Will we ever truly, quote 103, perhaps not in the way we find a new planet or discover a new particle. The, quote 104, might be an asymptotic truth, something we continually approach but never fully grasp, because to fully grasp it would be to transcend our own existence within this reality. But the pursuit, the ceaseless asking of questions, the awe and wonder that accompany each new discovery, that is the true reward. That is the essence of being human in a universe that constantly invites us to look deeper, to think bigger, to dream beyond the observable. The journey continues, my friends. The universe is waiting, and our minds are the perfect vehicles for this incredible, unending exploration. What profound truths will we uncover next? Only time and our relentless curiosity will tell. All right, my fellow cosmic adventurers, we've journeyed through the observable universe, peered into the vastness of the entire universe, imagined infinite parallel worlds in the multiverse, dipped our toes into higher dimensions, and even considered the mind-bending possibility that our reality might be a holographic projection or a sophisticated simulation. We've wrestled with the mysteries of dark matter and dark energy, pondered the very fabric of space-time, and dared to ask if consciousness itself is a fundamental ingredient of the cosmos. And in our last stop, we touched upon the most profound concept yet, the Gersten, quote 105, the Gerst des Kostes Gas 1-6, the Gerst des Kos 1-7 Jas, from which all existence, all laws, all consciousness might ultimately spring. Now, this is where our expedition truly enters uncharted territory, beyond the reach of even our most powerful telescopes or our most complex equations. We're moving beyond the what and the how of the universe and venturing into the realm of the why. A question that science, in its traditional form, often shies away from. But if we're truly exploring what's beyond the observable universe, then we must be brave enough to follow the logical threads, however speculative, to their ultimate conclusion. So, what is this, quote, 1-1-I? And how do we even begin to conceive of it? First, let's be clear. We're not talking about a physical place you can fly a spaceship to, or an entity with a beard sitting on a throne. This, quote 109, is, by its very definition, non-physical. It's not in the universe. It's what the universe, and perhaps all universes, emerge from. Think of it as the ultimate substrate, the fundamental canvas upon which all reality is painted. If information is truly the most fundamental aspect of reality, as we've explored with, quote 110 and the simulation hypothesis, then this, quote 111, is the source of all information. It's the ultimate library, the cosmic blueprint, the primordial data stream from which everything we perceive as real is generated. Imagine a boundless, timeless ocean of pure potentiality, not empty space, but pure possibility. Every physical law, every particle, every dimension, every conscious thought, all exist as latent potentials within this infinite sea. Our universe, with its specific laws and constants, is like a single wave that has crystallized out of this ocean, taking a particular form for a particular duration. And perhaps, as we discussed with Level 2 multiverses and eternal inflation, countless other waves, countless other universes are constantly forming and dissolving within this same inexhaustible ocean. This idea challenges our most deeply ingrained assumptions about reality. We're accustomed to thinking of existence as something that is concrete, tangible, measurable. But what if existence as we know it is an emergent property? What if the ground of being is something far more subtle, more abstract, something that precedes space, precedes time, precedes matter and energy? If this is true, then our concepts of before and after simply don't apply to it. The Big Bang marks the beginning of our universe, the start of our space-time. But the quote 15 isn't subject to these constraints. It is eternally existing in a state that defies our linear understanding of time. It's the ultimate Hassasses quote 116 from which all moments spring. And what about the quote 117 metaphor? If our universe is a simulation, then this quote 118 is the ultimate architect. But is it a conscious entity in the way we understand consciousness? Or is it something far grander, a cosmic intelligence so vast and alien that our minds can barely grasp its nature? Perhaps it's not a who, but a what, an ultimate self-organizing principle, an infinite algorithm that constantly generates and explores all possible realities. This takes us back to the profound connection between information and consciousness. If information is fundamental and the universe is an information processor, what if the ground of being is the ultimate consciousness? Not a consciousness within the universe, but the consciousness from which the universe, and all consciousness within it, arises. Think of it this way. If individual consciousnesses are like tiny windows looking out onto reality, then perhaps the ground of being is the entire boundless sky that all those windows are part of. Our individual awarenesses could be localized expressions, ripples, or fragments of this larger cosmic awareness. We are not just in the universe. We are, in a very real sense, the universe experiencing itself. This isn't a new idea, of course. Many ancient spiritual and philosophical traditions, from Eastern mysticism to Western idealism, have posited a fundamental, undifferentiated reality, or a universal consciousness from which all individual beings and phenomena emerge. What's truly fascinating is how some of the most cutting-edge speculative scientific theories are now beginning to echo these profound insights, albeit through the language of physics, information theory, and cosmology. So if we are indeed expressions of this ultimate consciousness, what is its purpose? Why does it manifest all of this? Why does anything exist at all when nothing seems like a perfectly valid, simpler option? This is the ultimate why question, the one that truly pushes the boundaries of our inquiry. Perhaps the purpose is simply to be, to experience the infinite tapestry of possibilities, to explore every permutation of existence, to witness itself through countless forms, from the simplest particle to the most complex conscious being, to evolve, to learn, to grow, not as an individual entity, but as an all-encompassing process of cosmic unfolding. Consider the anthropic principle again, but through this lens. If the universe is fine-tuned for life, And life, particularly conscious life, is how the ground of being experiences itself, then our existence isn't just a happy accident. It becomes an integral part of the cosmic drama, a necessary component for the ultimate reality to fully manifest and perceive its own grandeur. We are, in a sense, the universe's eyes and ears, its mind and heart. This leads us to a truly mind-bending thought. What if the universe isn't just expanding, but also waking up? What if consciousness isn't just a byproduct of complex brains, but a fundamental force that, through us, is bringing the universe into greater self-awareness? As we expand our understanding, as we ask these profound questions, are we not, in a way, helping the ground of being to understand itself? And if this ground of being is eternal and timeless, does it mean that universes are constantly being created and dissolved within it? A cosmic breath, inhaling and exhaling realities, each one a unique symphony of physical laws and emergent phenomena. Perhaps our Big Bang was just one such exhalation, and there have been, or will be, an infinite number of others, each with its own story, its own set of rules, its own conscious inhabitants experiencing their own unique slice of the ultimate reality. This isn't just about what's beyond our observable universe. It's about what's beyond the very concept of a universe. It's about the source code, the ultimate operating system, the boundless wellspring from which all forms of existence spring forth. It's the ultimate mystery, the ultimate truth, and perhaps the ultimate home. We've come full circle, haven't we? From the vastness of space to the profound depths of consciousness, we've pushed the limits of our perception, our understanding, and our imagination. We've explored ideas that sound like science fiction, yet are rooted in the logical extrapolations of our most rigorous scientific theories. We've acknowledged that the universe is not just stranger than we imagine, but stranger than we can imagine. And at the very edge of our understanding, we find not a blank wall, but an infinite vista. A vista where science, philosophy, and perhaps even a sense of the sacred begin to converge, hinting at a reality far richer, far more interconnected, and far more wondrous than we ever dared to dream. The journey beyond the observable universe is not just a journey through space, but a journey into the very heart of existence itself. And the most exciting part? We've only just begun to scratch the surface. The universe and its ultimate source remains an endless wellspring of wonder, inviting us to keep looking, keep questioning, and keep dreaming. What an incredible journey we've shared, hasn't it? From the familiar confines of our observable universe, we've ventured far beyond the edge of light, past the cosmic microwave background, and into realms that challenge our very understanding of existence. We've stretched our minds to grasp concepts that once belonged solely to the pages of science fiction, only to find them increasingly supported by the cutting edge of theoretical physics and cosmology. We began with the deceptively simple question, what lies beyond? And what we discovered was anything but simple. We learned that our observable universe, that vast 93 billion light-year expanse, is likely just a tiny, insignificant bubble in an infinite cosmos. Imagine that. Every star, every galaxy, every supercluster we can possibly see, all of it contained within a cosmic speck in an endless ocean. And this ocean, this entire universe, is so flat, so perfectly balanced, that it whispers tales of an explosive beginning, cosmic inflation, that stretched it to unimaginable scales in the blink of an eye. But that was just the beginning, wasn't it? This infinite expanse immediately opened the door to the multiverse. Not just one universe, but an infinite tapestry of them. We explored level 1, where statistical inevitability in an infinite universe means that everything that can happen will happen an infinite number of times. Somewhere out there, there's another you, reading this very sentence, perhaps even making a different choice for dinner tonight. Then we plunged into level 2, the frothing foam of eternal inflation, where our universe is but one bubble among an endless, ever-birthing collection, each potentially governed by its own unique set of physical laws. This helps us ponder the profound question of why our universe is so perfectly fine-tuned for life. Is it just luck? Or are we simply in a universe where the dice landed just right for us to exist and marvel at it? And then we dove even deeper into the quantum realm with level 3, the many worlds interpretation. Here, every single quantum event, every decision, every possibility doesn't just play out, but splits reality, creating parallel universes where every permutation of outcomes truly exists. It's mind-bending to consider that every path not taken by you, by me, by anything is still being walked in another reality right now. And if that wasn't enough, level 4 posits the existence of mathematical universes, where every consistent mathematical structure isn't just an abstract concept, but a real, existing universe. If it can be consistently described mathematically, it exists. Think about that for a moment. The implications are staggering. But our journey didn't stop at parallel realities. We dared to peer into the fabric of space-time itself, asking what lies beyond our familiar 3 spatial dimensions. This led us to the tantalizing possibility of higher dimensions, curled up so tightly we can't perceive them, as suggested by Kaluza-Klein theory and the elegant dance of string theory and M theory, with their 10 or 11 dimensions. And then came the truly radical idea of our brain-world models, where our entire universe is just a 3-dimensional membrane, a brain floating in a higher dimensional bulk. Gravity, the weakest of the fundamental forces, might be the only one that can leak into these extra dimensions, which could explain its feebleness. And if our universe is a brain, could there be other brains, other universes, existing just a hair's breadth away, parallel to our own, invisible to us? The thought is both terrifying and exhilarating. Then, just when we thought we had stretched our minds to their limits, we encountered the holographic principle. This isn't just about more space or more dimensions, it's about the nature of reality itself. What if our seemingly solid 3-dimensional universe is nothing more than a projection, a sophisticated rendering of information encoded on a distant 2-dimensional surface? Like a cosmic hologram, where the depth and solidity we perceive are emergent properties of a flatter, more fundamental reality. The ADS-CFT correspondence gives us a mathematical blueprint for this, suggesting that even gravity, that fundamental force, might not be a primary player but rather an emergent phenomenon. This naturally led us to the ultimate question. If reality is fundamentally informational, if it can be projected, then are we living in a simulation? Are we the products of an incredibly advanced civilization, or perhaps even an emergent property of the universe itself running through all possible realities? And let's not forget the profound mysteries that persist within our observable universe, acting as signposts to even deeper beyonds in our understanding. Dark matter and dark energy, the invisible architects and drivers of our cosmos, making up 95% of its mass energy budget. We know they're there because we see their effects, but their true nature remains stubbornly elusive. They are literally beyond our current grasp, hinting at entirely new physics, new particles, new forces that we have yet to discover. The quest for a theory of quantum gravity. To reconcile Einstein's majestic general relativity with the bizarre rules of quantum mechanics also points to a fundamental, quote 132. It suggests that space-time itself might not be the smooth, continuous fabric we perceive, but rather an emergent property arising from a quote 123 or discrete quote 134.4. Imagine that. The very stage upon which the cosmic drama unfolds might be an illusion, built from something far more fundamental. This brings us to the profound concept of quote 135. The idea that at the deepest, most fundamental level, reality isn't made of particles or fields or even space-time, but of information. Bits of information processed and interpreted give rise to everything we perceive. And if reality is information, then what about consciousness? Is it merely an emergent property of complex brains, or is it something far more fundamental, intrinsic to the very information processing of the cosmos? Panpsychism posits that consciousness, in some rudimentary form, is a fundamental aspect of reality, present throughout the universe. If consciousness is linked to information, and information is the bedrock of reality, then perhaps our own awareness isn't an accident, but a crucial component of the universe's self-understanding. This brings us to the precipice of the ultimate beyond. This isn't a place, or a dimension, or even a universe. It's a non-physical ground of being, a source of all information, from which all possible universes, all physical laws, all consciousness and all realities emerge. It's a timeless, boundless ocean of pure potentiality, an infinite algorithm exploring every conceivable reality, every possible set of parameters. Perhaps it's an ultimate cosmic consciousness, dreaming all of existence into being, or an infinitely complex computational system running through every possible permutation of information. And here's the truly awe-inspiring part. We are part of this grand cosmic exploration. Our insatiable curiosity, our relentless drive to ask, quote 138 and quote 139, is the universe's way of experiencing and understanding itself. We are the universe, observing and questioning its own nature. Every scientific discovery, every philosophical contemplation, every moment of wonder we feel gazing at the night sky is the cosmos reflecting upon itself, expanding its own awareness. So, where does our journey end? It doesn't. Not really. We've traversed conceptual landscapes that blur the lines between physics, philosophy, and even spirituality. We've pushed the boundaries of what we thought was possible, and in doing so we've found that the true beyond isn't just more space, but different dimensions, different realities, and a fundamentally different nature of existence. The ultimate mysteries remain unresolved, hanging in the cosmic ether, beckoning humanity to continue its endless exploration. We have only just begun to truly understand the depth and strangeness of reality. The observable universe, as magnificent as it is merely the opening chapter of an infinitely unfolding story. As we conclude this particular journey, I hope you feel a sense of profound wonder, a renewed curiosity about the cosmos, and perhaps even a deeper appreciation for the incredible, improbable fact of our own existence. We are living in a universe that is stranger, more vast and more interconnected than we could ever have imagined, and the adventure of discovery, the quest for what lies beyond, continues. It always will. Thank you for joining me on this incredible voyage. Keep looking up, keep asking questions, and keep dreaming big. Because the universe, in all its infinite glory, is waiting for us to discover its next secret. And who knows what profound truths we will uncover next? The beyond is not a destination, but an eternal invitation.